Welcome back. What we're going to do is continue with the OSI model we left off with the network. The next layer up, and we're just going from the bottom up, is the transport layer. Accepts data from the upper layers and breaks it into smaller units known as segments. Let me work into this right now. PDU, Protocol Data Units, what each of these things are called, which is something that you may need to know, but PDU and the mnemonic, I guess we do the PDU. The mnemonic that I use is don't some people fight back, which is going to be the data at the top here. Transport segments at the transport layer, packets at the network layer, frames at the data link layer, and then bits here at the physical layer. So don't for data, some, segments, people, fight back. So those are the PDUs, the Protocol Data Units. Protocol Data Units. That we can do this. So it accepts, the transport layer accepts data from the upper layers, the application presentation session, which eventually we're going to group together, but from the applications that run on the computer, and breaks it into smaller units known as segments. Passes these segments to the lower layers, transport segments, network packets, and ensures that all segments arrive correctly at the receiving end. The way it does that is, and we have all this other stuff here, it first initiates a connection at the transport layer using a SYN synchronization, a SYN-ACK, and the ACK goes with this SYN, a SYN-ACK, and then a synchronization and an acknowledgement. What this means is a synchronization says, hey, other end, I want to have a conversation, and here's my numbering system. So what this SYN is doing is actually creating the number system that we're going to use to number the packets. And then we acknowledge that synchronization, and the server that we're connecting to says, okay, but I need my own numbering system. So it sends us a synchronization, and then we acknowledge that. After that happens, we go into the sending and receiving of packets, and this is packet 0. I'm going to open a Wireshark TCP capture here in a second, take a little look at those. But packet 0, we send, receive packet 0, we acknowledge packet 0. What this says is send ACK 0, I acknowledge packet 0, send packet 1. So it sends packet 1, receive packet 1, send acknowledge 1. It sends 2, and we don't get 2, or we don't acknowledge 2. It sends packet 3. It discards, and then we send back an acknowledge 1, which says, hey, I got packet 1, send 2. On down the line until we actually get a resend on packet 2. It gets delivered, and then we can continue with the conversation. So what we do at this layer, at the transport layer, is ensure the reliability of the connection. Get rid of some of that stuff. So it adds a sequence number to each segment, which helps construct the original sequence of segments in case they're out of order. And that mess that we had earlier on the routers, if we had a whole bunch of routers and we had different paths and then we got some congestion, it might go one direction or the other, and the packets might arrive, and I'll use my own little numbering system. If we had packets 1, 2, 3, 4, and 5, they might arrive as 3, 5, 2, 1, 4. The numbering system would then allow us to put them back together as 1, 2, 3, 4, 5, so that the data made sense. Also responsible for error correction and sending acknowledgments at the network level. So it's going to acknowledge the receipt of the data packets when we do it. What I want to do, I'm going to pause here for a second, and I want to get a Wireshark up so you can see what it looks like. Okay, what I have on the screen now is a Wireshark capture, and this is the startup, what we talk about. We're going from, and we're going to have ports, and we're going to talk more about ports when we do TCP. In the next segment, we'll do TCP and UDP, the two primary transport layer protocols. But we have a link, we start, and where we're going, we have a send packet. The sequence number is the starting of the numbering system. And then down here, we have, and if you go over here, the IP addresses are the same that we're using, source and destination, and they flip source and destination when we answer. 667, and this acknowledges 668 because there's no data. When we actually have data, this increments based on the number of bytes of data that's in the packet. And then the other end sends its own sequence number and its send packet, and it's 663, and down here we acknowledge 664. So we start these things up, and then after we get going, the only thing we're going to have are acknowledgments. And if we don't get the information that we're supposed to, the data gets resent. So we go to the error correction. Transport's called, the TCP is called reliable. We're going to have two protocols here, TCP and UDP. TCP and UDP, and again we'll look at those in more detail the next time. Transmission control protocol and user datagram protocol. This is going to be connection oriented. Because of this, we create a connection. UDP is going to be called connectionless because we don't do this and we don't have any acknowledgments. But again, we'll discuss those in more depth in the next topic. The session layer, as we keep working our way up, controls the dialogue or the connections between computers. You might have multiple sessions when you're connecting somewhere. And we said earlier, you might have a web page open, an email client open, and maybe downloading something, or are connecting to Dropbox or Box or something else, where you have multiple sessions open, and the session layer controls those sessions, what gets resources at any one time. Establishes, manages, terminates connections between local and remote applications. Orderly shutdown of connections. Years ago, we had a NetWare server who had a problem. I think actually, as I recall, that it was running out of disk space. And occasionally it would just reboot for no apparent reason, which is really frustrating when you're trying to do a class and people are trying to do labs or tests or whatever else. But what we found out is once it restarted, if you would just sit at your workstation and let the system restart, it would bring you back to where you were. So the session layer was re-establishing those sessions when that happened there. Provides for full duplex, half duplex, and simplex operation. We've talked about those earlier. Full duplex, transmit and receive at the same time. Half duplex, we can transmit and receive, but only one at the same time. And then simplex operation is a broadcast arrangement. Establishes checkpointing, adjournment, termination, and restart procedures. The restart procedures, what I was talking about earlier. Responsible for the graceful close of the session. Orderly shutdown is typically what it's going to be called. Control the multiple bidirectional messages. It determines which session gets to talk, how long it gets to talk, how many times it gets to talk. Allows the presentation layer seamless view of the incoming stream. And when we're looking at an incoming stream, and when we do TCP, we can look at a TCP stream, the data, sequential data that we're going to get passed up to it from the transport layer. Presentation layer, and you'll notice as we get higher up into the OSI model that the layers go quicker. responsible for encoding data into a standard network compatible format. HTTP, PDF, and this is the one I talked about. Your browser may open a PDF, but if you get a doc file, you're probably going to have to download it because the network standard doesn't do it. The computer knows how to open a doc, but the network presentation layer may not. Standard data formats used to enable devices with different representation techniques to communicate with each other. Only an intermediary format and will change at the lower layers, going up and down. We go up and down with this thing. Define and negotiate data formats, ASCII, EBCDIC, binary, BCT, JPEG, whatever we're going to be using. And encryption is a service here, not HTTPS sort of encryption, because that's done different operation, but encryption as a service can be done here. Application layer, we're the closest to the user. Obviously it interfaces with the programs, network services to applications, email, file transfer, terminal emulation, web browsers. The different things are going to be running on the computer that are going to connect to and communicate with the TCP, IP, or UDP stack, whichever we're going to do, the OSI model that we're using here. Only to applications outside the OSI model, the application layer communicates. It's the only layer that communicates outside of the OSI model. Establishes the availability of communication partners, synchronizes and establishes agreement on procedures, and I want to underline this one because I've seen this other places. Establishes the availability of communication partners, synchronizes and establishes the agreement on procedures for error recovery and control of data integrity. Data integrity is what we send is what we got. And there are processes, and in security classes you can look at the process. We'll look at a hash to be sure that we have integrity. So what we want to do, data integrity, is to ensure that the data that was sent was the data that was received, that it was not changed en route. This is just another image that we talk about here, that we have same layer and adjacent layer. Same layer, which is the same layer. Each layer talks to its equivalent layer from source to destination. So the presentation talks to presentation, session to session, transport to transport, and on down the line. The adjacent layer is each layer supports the layer above it. So the data link layer supports the network layer. When we had the protocol routing, for lack of a better word, where if it was an IPv4, it sent it to the IPv4 network. And then the network layer, if it's TCP, send it to TCP. If it's UDP, send it to UDP. Session supports transport support session, and on up. So adjacent layer communication and same layer communication. When we get into data shipping that we talk about, the peer-to-peer at the fourth layer, once we create the connection with the three-way handshake, the SYN, the SYNAC, and the ACK, then we can ship the data to the network layer. The network layer, remember, is the one that finds the destination. So this would be, the routers would be here, and this shows here intermediate nodes would be the routers that have the network, data link, and physical layer that are going to ship the data from point A to point B. I think that does it for the OSI model. The next one is the TCP model. It does the same thing, but in a little bit different manner. And if you see here, I've got them side by side. The OSI model, the top three layers are the equivalent of the application layer in the TCP model. Makes things a little bit simpler. Application, we talked about, runs mostly on the computer itself. The transport layer is still going to be TCP. We're going to have the three-way handshake and all that all the other elements that go with it, except it's going to be host to host. Sometimes, and actually in the DoD model, it was still called the transport. So transport, host to host. The network layer, the inner network, is going to work exactly the same way as the network layer did. And then the data link and the physical layer combined as the network access layer. So this one, I'm going to go through the slides of these here in just a second, was developed to allow addition of new technologies and more flexible architecture, easily allow modifications of existing protocols, initially referred to as the DoD model, renamed after its two most important protocols, TCP and IP. So we have the TCP IP model as well as the OSI model. When we do these things, the link layer, the network access layer, is equivalent of both the physical and the data link layers. When we look at this thing, cables, connectors, network cards. One of the, I guess, kind of confusing aspects that we used to have when we just used the OSI model, we say what a NIC is a layer what device, and the answer was layer 2 because it had a MAC address, a physical address. But it also had the connectors to it. So it was a layer 1 device also. But when we combine these two as a network access layer, is no question. It combines both the physical and data link layers of the OSI. Cables, connectors, network cards like OSI. Layer 1 OSI model of the TCP is accepted with the hardware addresses, hardware MAC addresses, media access control addresses, 48-bit hexadecimal addresses. Let's see, the internet layer, the equivalent of the network layer, aligns directly with the layer 3 of the OSI network layer. Routes data source to the destination, so it finds paths. It's responsible for path discovery and using the most efficient path. It finds an addressing scheme, which is going to be IP either version 4 or version 6 today. Routing packets to remote hosts. Fragmentation and reassembly. Maybe fragmentation. The reason I say that is most packets are written today or marked today as do not fragment, because we can actually, as the hardware has gotten better, we can send larger and larger packets. The other issue is that fragmenting has a limited marking system, so that what hackers would do is insert their own fragments, because the only marking says more fragments or the last fragment. So it can become a risky situation. We don't want to do that, but fragmentation can occur. The data packets can occur at the internetwork layer. It's where IP operates, so we have IPv4 or IPv6, which are going to be addresses that can change. We have what kind of temporary addresses, IP addresses, and permanent addresses are MAC addresses. The host-to-host transport layer directly aligned with layer 4, TCP IP architecture. TCP and UDP operate here, three-way handshake, acknowledgement. If we're using TCP, UDP, we'll talk about a little bit later, but we have port numbers here. And if we go back to our Wireshark, here we have port numbers. Port numbers represent services that are running at the application layer. When we start up from our computer, my 192.168.100.150, it has a port number of 56744, a random port number, an ephemeral port number, temporary port number. It's going to port 80, which represents a web page, HTTP. So we have port numbers that operate here, and when we take an IP, and we'll do this again in the next one, and a port, we get a socket, which is a connection to a resource. So if we have, going to whatever 16.12.3.6 and port 80, we're going to the web server at that address. When I leave my machine, I might be at 192.168.150.7 and 57.366 or whatever. A random port number. Well-known port numbers represent well-known services: HTTP, FTP, POP3, IMAP, SMTP, SNMP. Bunch of different letters that we'll do, but they represent services that operate at the application layer. Application layer here, layers 5, 6, and 7 of the OSI, applications for file transfer, troubleshooting, internet activities. And again, this is not Microsoft Office. These are services that run at that layer. And then it supports network APIs, application programming interfaces, in order to do those things. Allows programs to access the network. Allows programs to access the network because at the application layer, remember, the one closest to the user that allows the computer to connect to the networking, sending data from point A to point B. Some protocols, we'll just introduce them here. They'll come and they'll go, but I don't think that you can ever start learning what the primary or popular protocols are. And so we'll look at the application layer, the things that are here: HTTP, a web server, port 80, FTP, file transfer protocol, port 21, Telnet, in order to connect, and we'll Telnet some, but what we'll really prefer is SSH, which is going to be a secure one, port 23, SMTP, simple mail transfer protocol, the sending, port 25, POP3, post office protocol, port 110. If we had IMAP, it'd be 143. And these are for the TCP, the send, the SYNAC, the connection-oriented applications that run there. UDP, user datagram protocol, which doesn't have the three-way handshake. DNS, port 53, SNMP, simple network management protocol, and this is one that the letters kind of look the same here, but they're radically different. SMTP is mail protocol, SNMP is going to be a management protocol, TCP, UDP. TFTP, trivial file transfer protocol, is port 69, which is a simplified version of FTP over here. NetBIOS, port 137, and then there's some others, but TCP and UDP, host to host, or the transport layer, are going to be here. The internet layer protocols, ICMP, ping, ARP, reverse ARP, BootP, DHCP, are things that are going to run down here, and this is going to be at the IP level. The network access, Ethernet, which is going to be a LAN protocol, FDDI, fiber, token ring is a LAN protocol, other protocols. We'll put in a couple of WAN ones here, PPP and HDLC. Ones that you're going to hear are WAN, wide area network protocol. So when we say, yeah, it's local, small network, big network, we actually do have technical definitions of those. So last slide here, layer models, and I think this is the same place that we started with, less complex compared to using the layered model. Network models break the concept into smaller parts so that it really does make troubleshooting easier when you start trying to find out why isn't the data getting from point A to point B, what's not working. Kind of like when your computer not working, doesn't come on. Well, power, no power. Okay, is there power to the outlet? Is the power supply good? Those sorts of things. We can do that. Same thing, modular on the computer. We can do modular by troubleshooting the communication process across the network from point A to point B. Standard interfaces, definitions between each layer allow multiple vendors to create products, fill a particular role with the benefits of the open competition. Easier to learn, even though it doesn't seem like it right now. can more easily discuss and learn about the many details of the protocol specification. Easier to develop, reduced complexity allows easier program changes, faster product development, program changes. Right now we're in a transition period between IP version 4 and IP version 6. The layered, model allows us to do that without changing everything else that goes on in there. Multi-vendor operability, I don't have to go get a Dell NIC if I want to add a network interface card to my device. Products meet the same standards, can go from one to the other, then modular engineering. One vendor writes software, but where at the higher level web browsers, and the other vendor can write the software that implements the lower levels. And this also allows devices from different vendors to be compatible with each other. So I'm going to quit there. That's the second half of the OSI and TCP, TCP/IP, and OSI models. The next topic is going to be to compare and contrast the TCP and the UDP protocols. So we'll see you there.